Thanks for having me on this jump day. I'm really looking forward to this topic in particular. I must have drawn the long straw because talking about model visualization is such a cool topic. And so I'm really excited to show you a bunch of things in JMP. Just like Mia did, I'm going to make a call out to a lot of learning resources. So as I go through today, I'm going to point out places where I hope you'll go and try to learn more. There is so much in JMP always that we could show you. And so I think of this really as me trying to show you the whole tapestry of things that are available within model visualization without going too deep in any one of them, but enough that you can see where it's going to be appropriate for your work. So just to give you a sense of where we're heading today, I'm going to start off by showing just a couple examples of what I mean by model visualization, but then we're going to dive pretty heavily into the prediction profilers in JMP. I'm going to talk about the types of profilers, model profiling specifically. I'm going to use a standard linear model, although profiling works all across JMP, even as Mia showed you. She showed you a prediction profiler, and it works really anywhere you're building a model. I'm going to stick to linear because it's something I think most of us understand, but of course remember that anything I show you here will extend into all the models in JMP. I'm going to then talk about some complex optimization. So times when you have a model built and you're trying to maximize some desirability, that is minimize some outcome or maximize or even hit some kind of target. And then I'm going to talk about a really neat application of the profilers, which is simulation, or in a specific way to actually simulate the outcome such that you can find more or less robust places to run your processes. And we're going to talk about a sort of a stochastic optimization problem. And we're going to do it in the sort of the process of using the profilers. So a really neat application there. But first, let me start, as you saw with Mia, showing what the prediction profilers look like. And so we're going to build out this particular prediction profiler. This is one from a standard linear model. And what we're going to do is play around with that as a way to understand our model coefficients. Certainly it's great for making predictions, but it's also a way to understand under the hood what your model is doing. Now there's actually multiple profilers in JMP. Another is the contour profiler. If you're familiar with reading topographical maps, this is the contour diagram, but instead of reading elevation, this will be reading your model's output. And so contour profiling is another great way to understand the way your model is making predictions. And finally, we're going to look at the surface profiler. We often tell people 3D is probably not that useful in addition to graphs, but in some cases it really is. And so the surface profiler is a great way to look at your model surface or the response plane, at least in 3 dimensions. We haven't figured out a 4-dimensional response plane, but we're not the only software company that doesn't do that. So 3 dimensions is where we're stuck. So let's start right in. I don't want to show you some static graphics. Let's play with the interactive versions. And to start, I just want to point out, again, there's lots of documentation here. I'm going to pull heavily from the JMP documentation, which is extremely well written. You'll see in my journal links to it. So if you pull that open, you'll find the pages where I'm referencing things. I really encourage you to look through this entire section. There's an entire book, in fact, on profilers. And so if anything I show you looks interesting, go check that out. But as I mentioned, there's a number of profilers in JMP, and we're going to look at a few that I mentioned right away. Now to start, let's actually set up a situation where we're trying to make some kind of prediction or building some kind of model. Now I think one that is pretty tractable for most of us is talking about something manifest or something that is familiar. And in this case, let's just talk about attributes of cars. This is some sample data that's in JMP. It's called Cars 1993. And we have multiple attributes of these different cars. Some of them are categorical, what model they are, what vehicle category they are. And some of them are quantitative, things like their city mileage in miles per gallon, horsepower, weight, so attributes of the cars. And what I want to do is build out a model using these data, predicting something that ostensibly we might care about maximizing, minimizing, or just care about understanding. In this case, let's use miles per gallon. And so what I'm going to do is I'm going to build a linear model using fit model. And to start, I'm just going to put, as we always do, our outcome variable as our y, and then build out some model effects. Now for this model, what I want to build out is a rather simple model, but one that has an interaction term, because one thing that profilers are great for showing are interactions or moderations of variables. It's actually the first thing that made me fall in love with JMP when I first started using it now about 15 years ago, was the profiler for understanding these bilinear interactions. So to build this model, I'm going to use the macro in the model effects section, and I'm going to do it as a full factorial. And if you're not familiar with that designation, what I'm doing here is fitting main effects, or effects that will test really the effect of that variable holding constant everything else in the model. So these are slopes in this case because they're continuous variables. And then an interaction term, which is really helping us understand to what degree does one variable, let's say horsepower, affect the outcome, miles per gallon, at different levels of weight. So specifically, does horsepower relate to mileage differently for light cars versus heavy cars? But it's doing this across the entire spectrum, so it's going to fit a coefficient that helps us understand that. Now, to help us just focus our attention, I'm going to choose minimal report, and I'm going to click run to run this model. And I'm going to hide my data table. Now, to clean up the output, because I want to focus our attention, I'm just going to hold down the Option key and click the red triangle. If you're on a Windows machine, you can hold down Alt. All this does is gives us all the options under the red triangle, and so I can toggle them all off at once. A little bit cleaner so we can focus our attention. Okay, so like I said, this model has a few parameters: the intercept or the grand intercept, the effects of horsepower and weight, and then that interaction term that's capturing to what degree one variable's level affects the relationship between y and the other variable. Now, before we dig into the model, I've tucked away something here that I think is kind of important, which is a graph that we can build out even before we look at the profiler as a way to understand this model, a graph that you can use to understand this relationship. And this is actually the way that when I was first coming to know JMP, I had always seen it in the literature. The way of showing a bilinear interaction is show a graph at the low level and the high level of the other two variables. And so let's just build that out quickly so we know what to expect here. So I'm going to go to Graph Builder, and I'm going to put mileage as my y. I'm going to put horsepower as my x. I'm going to toggle on a linear regression line. And what I'm going to do is use weight here to separate out the lines. Now, you may be familiar with Graph Builder. You can just drop it in the overlay role, and that will split out a variable, if it's quantitative, into 5 levels. I actually only want 2 levels, so I'm going to show you a quick trick. Drop it in the group for x, right-click, go to number of levels, and give it some other value. I'll give it 2. Now I can move it back to overlay, and now I have it split into low and high. Now, I realize that was kind of fast, but all we're really trying to do here is understand what our model is about to give us, which is a term that helps us understand the difference in these slopes. That is, for the cars that are light, there's a relationship between horsepower and mileage. Cars with more horsepower tend to have much lower miles per gallon. Interestingly, though, among the heavy cars, there's less of a relationship. That slope is less severe. And if we take a minute to think this through, and I think it's important we do because we're going to look at interpreting this in other scenarios, maybe it's the case that once a car is that heavy, 3,000 pounds, it's already getting crappy mileage. So maybe the horsepower differences aren't really hurting it much. And for the light cars, the ones that have low horsepower tend to be really like economy cars, and a really light car that has a lot of horsepower, well, that's probably a sports car. So maybe there's some ex post facto thing that we can come up with for reasons why this is the behavior. One thing's for sure, this is the data that we're working with. Low weight cars tend to have a relationship between horsepower and mileage, whereas heavy cars tend to not have that relationship. Okay, so remember that. Let's go back and look at our parameter estimates. There's a term in here that's capturing the nature of that interaction. And so we're going to come to understanding that in a second. And the way that's going to help us do that is the profiler. Now, as Mia showed you, under the red triangle, factor profiling, you'll find that profiler. You'll also find the other ones we're going to look at in a second. But let's turn on that main prediction profiler. And I'm just going to drag out the size just so we can focus our attention a little more clearly. Now, before I go any further, I want you to notice a couple things. The coefficient here, the one for horsepower, that is the slope of the line here, right? Negative 0.029722. That is saying, holding everything else constant at the average level in the model, the effect of horsepower on mileage is 1 additional horsepower takes away from mileage that amount. Similarly, the coefficient for weight, this very, very small value here, that is the slope at weight here. Holding everything else constant in the model, adding a little bit of weight takes away from mileage. So that's the negative slope there. Then we have this tiny coefficient, 5.38 times 10 to the negative fifth, right? That is capturing the interaction. And to see the interaction before we try to interpret it, what I want you to do is focus your attention on this plot on the left-hand side. Because what I'm going to do, as Mia showed you, you can change and do what-if analysis here. I can move around the weight of cars. I want you to focus on the relationship between horsepower and mileage, because what I'm going to do is play the game. What if we're talking about cars that are really light. Notice what happened. The slope of that line between mileage and horsepower increased, like increased in a negative direction. It became more severe, so it's a more negative slope. If I were to move weight to the heavy cars, right, that relationship flattens out. And this is what we saw in Graph Builder, right? This is just the nature of the data. But right now, we're profiling a model. We're profiling these parameters, the 4 that are in here. All of those capture what's happening in this model. And the real trick in this model is that this term, this maximum horsepower times weight, each of those have had their mean subtracted off. What that really says is as you move away from the mean, in one direction, you either add to the weight or add to the regression coefficient, or if you move away from the mean, you subtract from the regression coefficient. So it's tuning or moderating the effect of the other variable on y. And that's pretty cool. That's something we can see without ever having to even look at the parameter estimates. In fact, if you're not familiar with linear models, maybe you don't even want to have those on. And you can understand your model just by looking and playing around with these different prediction profiler levels. Now you'll see also, we can have the same effect. If I change horsepower to be very, very high, then weight doesn't seem to cast much of an effect on mileage. And if the horsepower is very low, the weight plays a big role. And again, this is the same term in that model. It's just showing us how the level of one variable affects the relationship between y and the level of the other. So the prediction profiler is not only a really awesome way to understand your models, but it's also a really great way to share them. So if you wanted to share this model with somebody and really help them understand the relationship, I mean, it's as simple as just going to File, Publish. I'll publish this to a file on my desktop. Let's build the report. And this will pop up in a window, and you could just share this profiler with somebody. In fact, I think it's probably one of the better ways to help people who are non-statisticians understand the way your model is making predictions. And so we're going to look at exporting a little bit later, but just know that these are things you can share with others. So a really, really neat use of that model. Now, before we go on to looking at this model in a number of different profilers in the other ones, I want to point out under the red triangle, there are so many things that you can do with this profiler. And this is what we're going to spend the majority of today talking about, the different options here. I'll point to a couple just rather quickly, which is the first, this idea of having a desirable outcome. So desirability functions in JMP relate to what response you really want from your y variable. So if I toggle on desirability functions, and I'm just going to make this window a little bit smaller so you can see it all, what we're looking at on the right-hand side here, right? If we imagine that line mapped across to mileage, what we're saying is that high miles per gallon are what we want, and low miles per gallon are not desirable at all. That's what that angle of the desirability function is. And then down at the bottom, these are showing us the levels of those variables, the factors that relate to high or low desirability. So it's more desirable to have a light car and more desirable to have a car with lower horsepower. What this all means is I can tell JMP, now that it knows what I want to be desirable or not desirable, I can tell it to maximize desirability. Search the factor space, and this is great for designed experiments. Search the factor space for the levels of the variable that lead to the highest desirability. And you'll notice in this model, it's rather simply low horsepower and a really light car. In fact, you don't even actually need to have the desirability functions on. I can toggle those off now that I've set the desirability, and I can still maximize my desirability. So for complicated models, I actually like turning those off because there's just a lot of screen savings there. I'll point out one more thing, which is now that I've done that, under my factor settings, I always like to say, remember settings. This is a nice way to keep a toggle for the settings you just put in. In this case, I'll say this is highest MPG. And now I get a little toggle here. And I can, set different levels. I can say at 250, let's set a setting here. And we'll say, remember settings. And this is setting where weight doesn't matter. I don't know, give it whatever you like. And the nice thing is these are now settings you can toggle if you, let's say, were demoing this to somebody and needed to share it. And in fact, just like I did before, if you publish this out to a file, those remembered settings will also be available. So it's a nice way, even if you're taking this with you or emailing it to somebody who doesn't have JMP, they can look at your desired settings. So we'll come back to that a little bit later, but it's a real useful addition to this. Okay, so that is the basic prediction profiler, a really valuable tool in and of itself to understand a model. But what I want to show you now are some other prediction profilers on this same model, now that we understand it, that'll help you understand different aspects of the model. And so I'm going to turn on a couple of them. I'm going to turn on first the surface profiler, which I'll show you in just a second. And I'm going to go back up and also turn on that contour profiler. And so these are two profilers we're going to check out. First, let's play around with the surface plot, because this is quite useful depending on the circumstance you're using it for. If you're trying to understand the curvature, or really really where the minima are, or your model in general, it's a nice way to look at your model. 3D does have downsides. It's hard to manipulate sometimes. You can't print it out. But if you're working with somebody in real time, it's a nice way to show off your model. Here's a couple tips. I tend to like to change the surface, so I right-click, go to Sheet Properties, and I much prefer a continuous gradient. What this is going to do is put a gradient high to low for based on the Y response levels. I tend to like a continuous gradient or sequential, so I'll toggle yellow to red. I also tend to like a mesh. I think it helps me see the three-dimensionality, and I tend to like that mesh to be black. There we go. And so now there's my mesh of my model. And so what's kind of neat here is this is showing the exact same thing that we were seeing in the prediction profiler. In fact, we can kind of understand the relationships we saw before. Remember, cars that were really heavy didn't have horsepower really mattering much because their gas mileage was already kind of bad. Let's turn on the grid here for weight. So I'm going to drag weight up for the really heavy cars. So if you look at that, that's the 3,700 pound cars. And if you look at across the ISO sheet here, across the surface, the slope is not that different. So I'll just put a response grid there. It's effectively showing me that across that plane going perpendicular, making the predictions, it's really not changing the Y response very much. And so the Y response is flat essentially there. But for cars that are really low in weight, so do it there, notice that my response grid, I have to drag up and down to follow the sheet orthogonal to that. Right? I'll even draw the line here for you. So drawing right here, that plane is now pitched rather heavily there. So that is showing essentially what the profiler showed me. Light cars tend to have a lot of effective horsepower in miles per gallon. Heavy cars don't. Right? So that same exact effect is being visible there. And truly, if you think about what your prediction profiler is doing, it's simply a cross-section or a slice of this response plane. In this case, our plane is two-dimensional, so it's easy to think of what a slice is. In higher dimensional models, it's still a plane. It's just a hyperplane, and you're taking a dimensional slice with the profiler. What is the effect of a particular factor at the levels you've dialed in of all your other factors? So I think that's pretty neat. And so I love the 3D profiler for really understanding your models. If you want to convince somebody you're doing a bunch of work, hold down the Shift key, just let it drag and let it spin on your desktop. That makes people think you're doing advanced stuff. So there's a tip for you to make it look like you're doing cool things. It is sometimes helpful, though, to leave it spinning to really help you understand the model. You can also hold the Shift key and then just hit an arrow key, and now it'll spin in the direction you pressed. So some things you can do with the profiler, or the 3D surface, I should say. Now, finally, speaking of profilers, let's talk about the contour profiler, which doesn't look like much right now, but we're going to add those contour lines just like topography so we can actually see the sort of the model in the same way we did before. And before we get there, I'll note that if you just are looking to optimize a particular target, like you want to get, no matter what, 25 miles to gallon for your car, if that's all you want, you can put that contour line in and then pick a value anywhere along that ridge, and that will be the miles per gallon for that weight and horsepower intersection. So that's all you want to do. That's a great way to do it. You can see the curvature because there's actually that interaction in the model. If there was no interaction, that would be a straight line across because the variables would have, in effect, be able to make up for each other. Now, if we want to understand curvature or the model in general, what I would recommend is go to the red triangle and go to the contour grid section. Because what this will let us do is put in a low and high value for our response, the Y variable, and an increment. I'll say do it in increments of 3 miles per gallon. And what it's going to draw for us is the contour lines. And so it's showing us our model, regardless of what level of miles per gallon we want, you can see it's incrementing up. And contour lines get closer, right, as the grade gets steeper. And so what we're seeing here is you can see where the minima is. So right there in the center, if you imagine that this is the fold of our surface, right? We're taking a three-dimensional thing and just folding it down. That's essentially the dead center. That's the lowest part of that plane. And again, that should make sense given what we saw before. Lowest miles per gallon tends to be a pretty heavy car with pretty high horsepower, and then moving off of that, interestingly, gives you higher mile per gallon. We're effectively extrapolating at a certain point. And if you want to see how ridiculous that is, if we drag out these models, apparently if you get a heavy enough car, adding horsepower gives you more miles per gallon. So don't extrapolate from your models. But that surface is kind of cool because now it's folded down as a contour. And so it gives you a sense of really the predictions of your model. And so I think the contour is pretty nice, the profiler. I use it a lot for showing off the three-dimensionality of a model if I have to print it. And for people who know how to read topographic maps, it tends to be useful. What I will say, though, almost uniformly, the prediction profiler, the main prediction profiler, gives you the most bang for your buck and gives you a lot of interactivity that when you're showing your models in person to people, I find to be really valuable. One final thing I'll say is you notice that when I drag around my prediction profiler, so let's say I have high levels of both, these profilers didn't line up, so I'm still set pretty low for both here and pretty high for those. There is an option that I like to turn on usually, which is allowing you to actually have the profilers linked. And so if you look under factor settings, there's this option to link profilers. And I'm going to do this for this talk, and I suspect you'll probably want to do this in general for yourself too. This will broadcast your profiler settings across any report, not even in the same window, across any report that shares those factor levels. And so linking profilers means now if I drag to that local minima, that place where there's the lowest miles per gallon, notice it does it for the others. So linking profiles, another pretty neat thing you can do. Okay, so I showed a couple things in this. The different profilers, obviously. I showed that we can do optimization, which is a pretty neat function and something we're going to explore a lot. And I showed that our profilers are really showing us the same things, but that you can deploy them depending on the circumstance you're in and what type of really audience you have. Certainly for myself, I use the prediction profiler the most, but the others are quite valuable. So what I want to do now is turn to some sort of extensions of what we saw to more complicated situations. The first I want to talk about is some complex optimization. Now, if you have interest in mixture models, I'll mention something you should read about definitely, which is the sort of the mixture algorithms and the desirability and profiling of mixtures. There's a great mastering jump as well for mixture models. And so these are models, not mixed models, but mixture models where you have multiple elements that have to sum up to some amount. So if you take a little bit more of one, you actually have to take away from the other. This happens a lot in physical chemistry. So the example I'm going to pull up is also in the sample data, but it's a plasticizer example. We're trying to optimize yield really or stability for a vinyl. And so these are ingredients for that vinyl. And so this is a mixture model. These have to add up to a certain thing. And oftentimes you'll look at things like ternary plots or mixture model plots for this. But what I want to show you is when I fit this model, I'm going to do it as minimal. And let's turn on our profiler for this. You'll notice that this is a rather complicated response here. And so there's some weirdness happening, right? As soon as and I'll make this a little bigger for those of you on smaller screens. As soon as I change the level of one of the plasticizers, notice that the levels of another variable have to change. And so as I drag these around, these are not independent. And this is a common thing with mixture models. And so optimizing is not as simple as it was in the last model where I could see very clearly that I can simply drag to the left on both of these. Now, desirability has already been set here. That's actually set as a property of my response, and so it knows what we're trying to optimize. That is, we just want this to be a higher Y value. But importantly for us, even though this is an incredibly more complicated situation, that optimization and desirability function works just the same. I can simply go to maximize desirability, and JMP will find the place of these different levels that will help me do that. Now, I'll mention there's important things you can do when you have constraints. So for instance, what if I know for some reason that I can only have maybe 0.5 of this first ingredient? So 0.50 is really what I have to have there. I can, on Mac, it's command click. On the Windows machine, it'll be control click. I can click on that profiler and lock that factor setting. And so I can tell the optimizer, you can't play with that. I want you to tell me the optimal values of the others to maximize Y while holding that constant. And so if I do that, I can maximize desirability. It can't move much, and these are a pretty constrained space, but it still finds that maximum. And you'll notice that it can't even predict out from here because locking that factor setting in a mixture model is constraining the elements based on the linear constraints of the other ingredients of this mixture. And so the profiler is very smart about what it knows is possible and how to do that optimization algorithm. And so that's just a quick example, but I invite you, especially if you're working with mixture models, to look more into that. Now we're going to stick with the optimization idea, but I want to show it to you in the context of some simulation, specifically some stochastic optimization. And I will say, if this is something that grabs you and you want to learn more, there's a bunch of things I want to point you to. The simulator documentation has a lot in here about the example I'm going to show you. And so definitely go to that link. And in fact, if you're reading the profiler documentation, you'll find it right away. It's quite great. But you can also look at two talks. These are by my colleague, Robert Anderson. One was a discovery presentation in 2016. The other was on Jump on Air a couple of months ago, a shorter one. And they're called the Simulation Experiment and the Robust Optimization Discovery Presentation. Check those out. Robert does a great job going through a kind of similar example, but in a lot more detail than I am about to. But my purpose here is I want to make sure you get a sense of what you can do here and the value of it. Okay. So let's start off with the basic idea. What we have is, based on some knowledge of physical chemistry, we know how yield functions as a relation to reaction time and reaction temperature. In this particular example, we're trying to optimize the yield of kind of an in-between ingredient. A reacts to get to B, and B we have as a reagent to get to C. Doesn't matter too much for our example, but what we're trying to do is maximize this yield. And we understand how to do it based on actual physical laws, so we can effectively do it noise-free. But we need to find the amount of sort of time and temperature to have for these ingredients. And we want to maximize based on the knobs we can turn with those. And so what I'm going to do is bring open the profiler. This is just a small profiler. And I'm going to make it bigger so we can kind of look at playing around with this. You'll notice as I move around reaction temperature, my relationship between reaction time and yield is changing quite a bit. And let's just give some names for ourselves, just so we can think about this. I'm going to call the left-hand side cool and the right-hand side hot. We're talking about Kelvin here, so everything is pretty darn hot. So 540 minus 273.5, we're still talking above 200 Celsius. So it's all very hot, but cooler and hotter. And on the right-hand side, let's talk about quick versus long reaction time. Of course, these are all in less than a second, 0.15 to 0.29 seconds. So it's all very fast, but short and fast. Long and slow. I said the same thing twice. Fast or slow, and cold and hot. Now, if I'm running hot, notice that for reaction time, the best thing I can do is do this very quick. So I can do hot and fast. That seems like it's optimal. Or if I'm on the long side, slow, the best thing I can do is cook it at a lower temperature. And this sort of makes sense if you think about baking anything. You can either cook it really hot for a short amount of time or cook it at a lower temperature for a longer time. And those seem like they both give pretty good yield. Now, we can use the optimizer, and I'll do that, maximize desirability. And what Jump says is the best you can do, the best yield, 0.621252, is that rather short reaction time at a high temperature. So hot and fast. Like we learned before, let's save that. I'm going to go to factor settings and remember. And so this is highest yield. Highest yield based on the optimizer here. But let's imagine that we cannot perfectly control these things. Reaction temperature, maybe our oven has some variation, and time, maybe at levels that are this fast, we can't perfectly control that. And so what I want to do is turn on what's called the simulator. And so if you go to the red triangle for the profiler, simulator is right here, which allows us to do Monte Carlo simulations right inside this graphical profiler. Now, there's a lot of options here, things that we could talk at length about, not to least of which is that you have all these different functions around sort of the type of variation you can experience within each of these different factors. Normal weighted is what I have dialed in here, and so we'll just leave all of that the same. But what I want you to imagine is what would happen if we had this amount of variation, the variation here as drawn by these normal distributions, if that variation occurred over a long number of trials. So if we were to try this reaction maybe 12,000 times, if I were to keep running this experiment and keep doing this and measure the yield, what would happen? Well, we don't have to do that. I could just click simulate, and what JMP will do is simulate that distribution. It's showing it to it as a vertical distribution. And so we see that most of the time, we're getting actually pretty darn high yields. The mean is right there. That's the 0.62152. But we have a bit of a tail. There are times where we unluckily drew reaction time and temperature combinations that tended to produce pretty bad yield. We have actually a spec limit already set for this column. So the rate of time that we produce a batch that's not proper or doesn't work for us is about 5% of the time. If I keep clicking simulate, you'll see I get different values. This is a Monte Carlo simulation. It's running this randomly. So it varies around there, but I would be comfortable saying 6% of the time, we're going to get a batch that's not good for us because of this. Maybe that's fine for us. Maybe that's within our tolerance, but maybe it's not. And the question is, are there other places here within this process where we could find a better maximum? A maximum that maybe is even a little bit lower in yield, but less noisy. And I'm going to sort of jump and give away the story a little bit. What happens if we do that longer and lower temperature cooking time, the cooler, slower cooking? So if we move out here, let's say to 0.2 for the reaction time, I have to select right here. The yield is going to be lower, 0.608. But watch what happens when I simulate. I've now dropped my failure rate to less than 0.5%. And it's happened because I've certainly lowered the yield, but I've reduced the effect of the variation on my surface or on my outcome. And we can understand how that's happening. I'll again jump to it rather quickly. If I jump to the surface, what I've done is move myself from, let me actually draw these in. So if I have my very hot and very fast reaction, I'm right at this intersection. And notice that any variation around there, I fall off a cliff, right? I fall off the edge of that peak. But if I do the low and slow, so lower temperature at a slightly longer time, I may have a little bit lower of a yield, but I have more buffer. I have more sort of tolerance of falling off the side or getting a little bit of noise in the system. That is, the yield doesn't drop off so precipitously. And so what we've just discovered is that there's a more stable place for us to run our process. I've done it by guessing and checking, which doesn't seem like the best thing we should be doing, but we can see that one exists. And so now that we have that proof that there's potentially a better place if we can't control these factors, let's figure out how to find that better place, because guessing and checking is never the way to do it in something as sophisticated as JMP. The way to do it is what's called a simulation experiment or stochastic optimization. And what we're going to do under this simulator is select simulation experiment. And what this is going to do is give us the option of essentially filling out the factor space with random picks, running those 12,000 simulations, right? When I click the simulate button, that ran 12,000 trials to give me a defect rate. Imagine doing that, let's say 80 times, and we're going to fill out the entire factor space. So I'm telling JMP to use the entire range it has observed of those variables. And pick 80, just use a space filling design or a hypercube or something if it's 3 dimensions, but it's only 2, so just a space filling design. Pick values for our factors that fill the space, and then run that 12,000 for each of those different points. Seems like that should take a long time. JMP is very fast, my computer is very fast. This takes it only a few moments, and now it's run 12,000 times 80 runs of this experiment. And it's produced for each of them what that defect rate was for the yield. So if I were to put in these 2 temperatures right in here and click simulate, it would have given me that value, that defect rate. It's just done the work for us. All right, at this point, it's kind of dealer's choice how you want to work with this. What we have is a log 10 for the defect rate, or we have the actual raw defect rate. In whatever case, we're just trying to minimize defects. And so as Mia showed, neurals do very well. I used to do this often with a neural network. So predicting the defect rate using reaction time. And what we can actually do is just fit a model that tries to minimize that defect rate. I'm doing this rather fast because I want to show you the built-in script. But effectively, we can use the profiler, use the optimization, so maximizing desirability. Remember, we can always maximize desirability. If we want to minimize defect rates, we can let JMP find the place where we minimize the log 10 of defect rates. Really quite cool. Now, there is actually a better model for this, and it's the one that's stored in the table, called the Gaussian process. You all have JMP Pro, so you get to take advantage of something special with Gaussian process. So I'm going to go into launching the platform myself, actually. I'll put log 10 as the defect rate, reaction time, and temperature. You can use fast GASP. This is actually going to multi-thread Gaussian process. Gaussian process can take quite a long time to fit sometimes. JMP Pro lets you multi-thread it or parallelize the process. And now it does it basically as fast as a neural can fit, which is incredible. So I'm going to turn on the profiler here and do the same thing. Optimize, maximize desirability. While that's doing it, remember what this is doing. This is searching the space now of our factor space to look for the place that has the least defects. Not maximizing yield. We don't totally care about that in this scenario. We care about defect rate. And so it's searching that factor space, and it's found a reaction temperature and a reaction time that minimizes defects. Now, what's kind of cool, remember when I linked my profilers before? What it has done is linked the profilers even across these two. And so that 528 point blah, 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 that's already in my original profiler. So if I click simulate, notice that I've gotten that yield a little bit lower, but the rate of defects is now to 0.1%. Right, so that is, I'm very confident, the place within this factor space that I should be running this process if, in fact, I can't control these knobs as well as I would hope. If I do experience noise in setting the temperature and setting the reaction time. And so stochastic optimization is really cool, right? I was able to, without doing the guessing and checking, produce those experiments that'll actually try to optimize the thing I do care about, not just yield, but in fact here, the defect rate. And so that's just one thing available under the simulator. I'll mention there's just so much more here that you can read into if this is the type of thing you work on. And so I'll just do one last thing before we leave this example. Now that we're at this point that lowers the defect rate, I'm going to remember the settings and say lowest defect. And just so we can see everything on the screen, I'll turn off the simulator. We've used it for all it's worth. And notice now we can toggle between these two. So highest yield and lowest defects, very different places within those surfaces. And what I'll say is, if we look at the difference here, we've sacrificed a little yield. It's showing us the difference between these two. You know, we sacrificed 0.018 in the yield, but we've done so much better for the defect rate, from 5% to effectively 0.1%. And so simulation and stochastic optimization, something you should really look into if you do this type of work. All right. Now, before we leave the simulation section, I do want to mention that we've so far only done model simulation. You've had some model, you've built some terms, and you built some prediction, and now you're trying to optimize. You don't actually have to do that. Profilers are a very general optimization engine within JMP. You can even access them totally from JSL if you want, or the custom profiler. And so the custom profiler under the graph menu, you don't even need to have a graph here. You can just feed it algorithms or feed it formulas you want to optimize. Now, I'm going to show you an example. This one I pulled directly from the documentation so you can expand on it further. But this is just an example simulating some general formulas. And so what I've built out here is a table. Imagine we're predicting sales for our new company, right? So what I've done is for all the various inputs into this process and outputs, I've put ranges that I want this modeling to take into account. So unit sales from 1,000 to 2,000, a range of what we're actually going to charge people for this same thing we're building, a cost for us to make it, our revenue, the total cost, and profit. Now, these final three, these are formulas, you'll see, because they have the big plus sign there. And so revenue, right, that's unit sales times price, simple formula. The total cost we experience is unit sales times cost, plus some baseline. Maybe that's the cost of us paying the injection molding company for making these little widgets that we're making. Whatever it is, that is a fixed cost that we have to surmount. And then profit here is revenue minus total cost. Now, all I've done in this profiler, I've just gone to graph, gone to profiler, and fed in my formulas. And so I said, give me a profiler that understands how to use revenue, cost, and profit. And it spit out this little profiler because JMP knows with those formulas how to actually work on these. And so I'll just expand these out a little bit and so we can see. And now if I imagine sales going up, I can see how profit changes. Or if my unit sales are very low, I can see my profit's pretty darn low, right? So this is giving me a sense of the sort of the different inputs to the system. Now that's all well and good and fun we can play with, but the simulator is where this is going to become quite interesting. So I'll go to the red triangle for the prediction profiler and turn on the simulator. And let's imagine that we don't have, we have total control over the price, let's say, but we don't have total control over the cost. So let's just say there's a random element to how much it'll cost us to make these little widgets. And we don't have total control over how much sales we have. Maybe we have an idea of what the sales will be, but we think maybe it's, I don't know, let's say it's fixed, and let's give it a uniform distribution between maybe 1,000 and 2,000, right? We think that's going to be our sales somewhere within that range, but otherwise we don't know. Now, 0 is the lower spec limit or the line here. And so what we hope is that for none of the simulations I'm about to run, I get a value lower than 0. That means that I have a chance of actually not making a profit when we go to market here. And so if I click simulate, notice we have a lot of that distribution spanning over the 0 line. In fact, if we look at the rate, 62% of simulations out of the 5,000 that just ran occurred with us getting less than 0 profit. Not good if we're going to market with this as the cost we're charging. Now, unless we can change the cost of building the unit or make more people buy it, which maybe we could, the thing we have control over is the unit price. So based on the simulation, we can't charge $3 for this. We have to charge maybe $3.25. And let's simulate that. Now, if we do that, only 20% chance based on the simulations we would actually fail to make profit. All right, let's bump it up a little bit, $3.50. Will we feel comfortable that we're not going to make no profit? Okay, in that case, 1.7% of the time, or a rate of 0.0172, we had a simulation based on draws from these distributions where we didn't make a profit. The rest of the time, we at least made some profit, overcame our costs and our revenue. So this would have actually been a kind of hard thing to script out or to simulate on your back of the notebooks. You could do it, you could figure out the occurrences at the extremes, but actually running the simulation would be quite hard. And so this is just a great example of even things that are rather simple models. If there's some random element to it, you can actually get a much better answer just by using the simulator within JMP. And so I think that was a pretty neat example of that one. All right, I'll close the sales model here. Now, I will mention that these, again, were part of the documentation, those stochastic optimization and the sales model. So I'll just point that again. The simulator doc here also goes into a lot of detail, especially if you need to show off these models or the simulation to others. There's probably a lot you'll want to know about sort of the statistical details that go into this. And there's lots of situations where you can use this beyond which I just showed you. So within certainly defect sampling or any kind of control charts or any kind of control situation where you're trying to manage the number of misses for out of spec units, that kind of thing. Simulation is a really great place to go, especially because you're able to tune those distributions based on what you expect to be the prevailing amount of noise in the systems you have. And so certainly look into them as an option, especially when you have these systems that, are not perfectly controlled by you. Now, in the last minute or two, before we jump into some questions, if there are any, I do want to do a couple of bonus things because I heard that you all got JMP Pro recently, and so there's a couple simulation and bootstrapping things that are in JMP Pro that you may not have heard about. And to show you, I'm just going to pull back that cars example because these are rather quick to show. The first is the right-click bootstrap, which is effectively resampling techniques to get confidence intervals or to get bounds on a statistic when perhaps there's no closed form solutions for them. Let me show you what I mean. So let's say we're looking at city mileage, and let's say the thing you care about most with city mileage is not the mean, which we have a confidence interval on, but let's say you care most about the interquartile range, and you want a confidence limit on the interquartile range. which is a rather strange thing to want a statistic or a confidence limit on. In fact, it's so strange that there's not even good solutions for how to find that. So in JMP Pro, which you all have, you can actually anywhere inside of JMP, with very few exceptions, you can right-click on the statistic, and you'll notice now you have two options. You have a simulate, and you have a bootstrap. Bootstrap will pop up a window here where it says, well, how many samples do you want? How many times do you want me to go back to the table and take a random sample of those observations? It can do it in clever ways. Fractional weights is a nice way to do it, where it actually fractionalizes each of the observations and then takes the sum or takes the statistic you're actually interested in. I'm going to leave that on, and I'm going to do it for, let's say, 500 bootstrap samples. And what it's doing is every time it runs this little iteration, it's going to go to my table, pick fractional weights for each of them, run distribution, calculate the interquartile range, and save that value to the table. Actually, it's going to save all the values that I have in that particular column. It's going to keep doing that over and over and over until we get to 500 iterations. And if you think about that, by bootstrapping the statistic, we get a sense of the sampling distribution of the interquartile range, or whatever the thing is we want to know. And so there's my interquartile range, and I'm going to go to distribution. Before I do that, actually, let's orient you. We have 501 rows in this table. We asked for 500 bootstrap samples. The first is the original sample. That's our actual sample and the statistics that were in that column. The rest of these are from the bootstraps, so from the resampling of those observations within the table, the fractionalized ones. I'm going to go to distribution. I'm going to use the interquartile range now. And what JMP is showing me, this is the observations of the interquartile range calculated for each of those bootstrap samples. And so we actually have the range. We can look at them, the median, the mean. These are all statistics of the interquartile range. And because JMP knows that this is a bootstrap sample table, it's already added us a new section, the bootstrap confidence limits. And so if we wanted a 95% confidence interval for the interquartile range, we could actually report it's 7 to 10. The observed interquartile range was, in this case, a 7. And so the bootstrap lower and upper is 7 to 10. Pretty neat, and allows us to add those confidence limits on truly any statistic within JMP that allows the bootstrap. So the only platforms that really don't do that are things like mixed models for good reason based on how they're calculated. So that's the bootstrap. So think of that in your arsenal whenever you need to add a statistic around a statistic. So a confidence limit, for instance, or you want the range of that based on bootstraps, or you just want to look at the stability of that. So slightly different from the bootstrap is the simulate option. And to show you that, I'm going to go to a pretty common sample data table that we all know and love. So our big class sample data table. And the reason why is I want to show you an application of the simulate that is often used, or one that we've seen valuable, which is using it to do permutation tests. And so to sort of motivate this, let's imagine we're looking at sex as our factor, and we're looking at the heights of individuals in this class. So if I turn on, let's say, a t-test, right, I get a p-value for this. Under the null hypothesis, how unlikely is the difference we observe, in this case, what is it, 3.02, or more extreme. And so that p-value helps us make an assessment. Do we think the difference is big enough that we should reject the null, that we should think that there actually truly are differences in the population from which the sample is drawn? Okay, that makes a lot of assumptions. It makes assumptions about the normality of the population. It makes assumptions about the equal variances of these two different groups. It's making assumptions that maybe we can't always uphold, especially if we have small samples and we can't check those assumptions. So a permutation test allows us to relax distributional assumptions, the assumption that the population is actually normally distributed. And we can relax that because rather than relying on a large sample approximation to the sampling distribution, we can actually simulate the sampling distribution by creating the as-if situation in our data table of a null hypothesis. Let me show you what that looks like in practice. What I'm going to do is I'm going to take the height column, the one that I'm actually testing. I'm going to right-click on it in the table, go to New Formula column. I'm going to go to Random, and I'm going to select Sample Without Replacement. What this does is every time this formula runs, and I can show you I can run it and we'll get something different. Every time that runs, that shuffle of height column is shuffling the values in that column. So truly, if I were to think about the hypothesis that the shuffled heights differ by females and males in this data table, truly there is no difference, because theoretically, I'm just shuffling the values. There couldn't be a systematic difference between the labels F and M in this table because I've randomized the outcomes. There may be on any one iteration of the randomization, but in theory, the population in this case is null. There's no difference between M's and F in my table now. So what simulate lets me do is pick a statistic. I'm going to use the difference here. I'm going to right click and simulate. And what I'm going to tell JMP to do is, well, substitute in height, the real variable I used in this analysis, and run that reshuffling however many times I specify. Let's do 500. Run that reshuffling that many times, and every time you do a shuffle, which should return a distribution where there's no difference between men and women in this case, or males and females, every time you do that shuffle, record the difference value. How different are the groups that have been randomly generated in this case? And so it's going to do that 500 times and build us, just like the Bootstrap did, a table showing us those difference values. Here's the cool part. Let's look at the distribution of the differences. So this distribution, if we look at it, it is fairly normal. It should be. These are coming from a normal population generally. But what we have are simulation results. Again, JMP knows this comes from a simulated table, so it's added on special things. I'll point out something before we look at the simulation results, which is that right here, this value that is marked, right, that is actually 3 point whatever. That's the original estimate for the difference, 3.0, I think it was. 3.02, there it is, it's right there. That difference, if we look at where it occurs in now the sampling distribution under the null hypothesis, it's fairly extreme. Of the 500 times we resampled or shuffled that column, of the 500 times we did that, very few times did we happen to place individuals in the M and F categories such that the difference between them on average was beyond the original sample. So let that sink in for a second. It's very unlikely, if we're just randomly assorting the values, it's very unlikely that we would make groups where they differed at 3.02 or more. Or I'll say it in terms of a p-value. Under the null hypothesis, where there is no difference, how unlikely is it to get the observed sample difference, the original, or one more extreme? Well, that's just an empirical p-value. We built the empirical sampling distribution, and we have an empirical p-value now, 0.0200. That is the proportion of times in this resampling that we found a sample based on random assortment that exceeded the original sample estimate. So we've done a simulation of the null hypothesis, and we built out a sampling distribution with 0 parametric assumptions. So we can utilize this type of permutation test really any time we can't make an assumption about the population distributions, which is an incredibly powerful tool in our arsenal. I will say it still requires weak exchangeability under the null hypothesis. Just means that the distribution variances should be the same, just like our normal assumptions are, but we don't need to care about the shape of the populations. And there are plenty of times where we don't know the population shapes and we don't have a sample size large enough to rely on the central limit theorem to bail us out. So permutation testing ends up being a really important thing that you get with your JMP Pro license, among all the other things you can use the right-click simulate for. But this is one you can effectively use anytime you do a hypothesis test and you don't want to assume a normal population. Okay. So that was a little just bonus because you all have JMP Pro, which is a great addition. But we covered a whole lot. So I do want to make sure you look at the profiler docs. There's so much in there, and the documentation is so well written. And so please check it out. And I hope you've seen something that you can use. And I'm definitely happy to answer any questions now if there are any.